In this chapter, the topic of stoichiometry will be discussed. Stoichiometry is the calculation of quantities in chemical reactions. Let's look at an example. Ammonia is produced by the reaction of nitrogen with hydrogen. In a balanced equation, one molecule of nitrogen gas reacts with 3 molecules of hydrogen gas to form 2 molecules of ammonia gas. Remember, the number and type of atoms are not changed in a reaction. When we look at the number of molecules, we know that the ratio of nitrogen to hydrogen to ammonia will always be 1 to 3 to 2. If we multiply the number of molecules involved in this reaction by Avogadro's number, we notice that the total number of moles of reactants doesn't have to be equal to the total number of moles of product. An important law in chemistry is the conservation of mass. Mass is neither created or destroyed in a chemical process. Therefore, the total mass of atoms does not change in a chemical reaction. Assuming standard pressure and temperature conditions, we notice that the total volume of the reactants at STP conditions doesn't have to be equal to the total volume of product at STP conditions. For the ammonia reaction, we can define several mole ratios. A mole ratio is a conversion factor obtained by interpreting the coefficients of a balanced chemical equation. Mole ratios can be used in chemical calculations. Let's illustrate this with an example. How many moles of ammonia can be produced using 0.6 moles of nitrogen gas? 1 mole of nitrogen gas can produce 2 moles of ammonia gas, mole ratio equal of 2 to 1. Therefore, 0.6 moles of nitrogen gas can produce 1.2 moles of ammonia gas, since the mole ratio must be 2 to 1. Mole ratios can be used in mass-mass chemical calculations. Let's illustrate this with an example. How many grams of ammonia gas can be produced using 5.40 grams hydrogen gas? First, we need to convert the mass of hydrogen gas into moles of hydrogen gas. 5.4 grams is equal to 2.7 moles of hydrogen gas. Then use the appropriate mole ratio. 3 moles of hydrogen gas can produce 2 moles of ammonia gas. Finally, we need to convert the moles of ammonia gas into grams of ammonia gas. The mole-particle relationship can be used to convert particles to moles and vice versa, using the fact that 1 mole contains a number of particles equal to Avogadro's number. The mole-volume relationship can be used to convert volume to moles and vice versa, using the fact that 1 mole is equal to 22.4 liter, at STP conditions only. Let's illustrate this with an example. How many milliliters of oxygen gas are needed to produce 20.4 milliliters of sulfur trioxide gas, at STP conditions, according to the following balanced equation? We know that 22.4 liter of oxygen gas, which is equal to 1 mole, will produce 44.8 liter of sulfur trioxide gas, which is equal to 2 moles. It's easy to show that 20.4 milliliters of sulfur trioxide gas requires 10.2 milliliters of oxygen gas. Limiting reagent is the reactant that determines the amount of product that forms, and will be completely used up after reaction. Excess reagent is the reactant that is not completely used up after reaction. Let's look at the reaction to produce ammonia gas from nitrogen gas and hydrogen gas. Let's assume that before the reaction, there is 3 moles of nitrogen gas and 6 moles of hydrogen gas. With these amount of reactants, we can only form 4 moles of ammonia gas. So, after reaction, there will be 1 mole of unreacted nitrogen gas, while all hydrogen gas molecules are used up completely. Conclusion. In this example, hydrogen gas is the limiting reagent and nitrogen gas is the excess reagent. Example. Given the balanced equation for the incomplete combustion of ethene. If 2.7 moles ethene reacts with 6.3 moles oxygen gas, what is the limiting reagent and how many moles of water are produced? From the balanced equation, we know that 1 mole of ethene reacts with 2 moles of oxygen gas. Since the mole ratio is a constant, 2.7 moles of ethene react with 5.4 moles of oxygen gas. As 6.3 moles oxygen is available before the reaction, ethene is the limiting reagent. From the balanced equation, we know that 1 mole ethene produces 2 moles of water. Consequently, 2.7 moles of ethene will produce 5.4 moles of water. The percent yield is defined as the ratio of the actual yield to the theoretical yield times 100%. The theoretical yield is the maximum amount of product that could be formed from given amounts of reactants. The actual yield is the actual amount of product that was formed by a reaction. Several factors may affect the percent yield, such as reactions do not always go to completion, impure reactants and competing side reactions, laboratory procedures. Let's calculate the percent yield in an example. If 50 grams of silicon dioxide is heated with an excess of carbon, 27.9 grams of silicon carbide is formed. What is the percent yield of this reaction? From the balanced reaction, we know that the mole ratio of silicon carbide to silicon dioxide is 1 mole to 1 mole. Step 1. Calculate how many moles there are in 50 grams silicon dioxide. Step 2. An equal amount of moles of silicon carbide will form theoretically. Step 3. Calculate the mass of silicon carbide that will form theoretically. Step 4. Calculate the percent yield of this reaction.